In this video, we're going to talk about applications of Maclaurin series. I'm going to give you two examples of two different ways in which you can use Maclaurin series. The first one is going to be how to use Maclaurin series to calculate limits. And the second one, we're going to introduce the concept of a differential equation and how to use Maclaurin series to solve differential equations. In our first example, we are going to use Maclaurin series to calculate the limit when x goes to 0 of cosine of x minus 1 plus x squared over 2 over x power 4. Now, if you check for x equals to 0, you would get cosine of 0 minus 1 plus 0 over 2, which is 0 in total, and the denominator is also 0 if you evaluate it. So this limit could be easily solved with L'Hopital's rule. So by no means I am saying that limits like this can only be solved by Maclaurin series. It's just one additional method that you have if you are willing to do a little bit of more work or if you're not familiar with L'Hopital's rule. So the first thing you want to do is you want to take your limit and you want to substitute the Maclaurin expansion of cosine of x. That means the limit when x goes to 0 of cosine of x minus 1 x squared over 2 over x power 4 can be written as 1 minus x power 2 over 2 factorial plus x power 4 over 4 factorial minus etc. minus 1 plus x power 2 over 2 over x power 4. What I can do next is I can cross out 1 and minus 1. I can cross out x power 2 over 2 with x power 2 over 2. And so my limit would simplify to x power 4 over 4 factorial minus, and we know the next one would be x power 6 over 6 factorial plus x power 8 over 8 factorial, etc. And then in the denominator, we still have x to the power of 4. So what we can do next is we can factorize x to the power of 4 and simplify it with the denominator. So when we evaluate our limit, all of the terms that have x will disappear, and the only remaining term would be the 1 over 4 factorial. Our next example is the solution of a differential equation approximating the function by the next application is the use of Maclaurin series to solve or approximate the solution to a differential equation. A differential equation is going to be a mathematical relation like this one that will relates the function with its derivatives. Now, this differential equation only contains the function y and the first derivative, so it's a first degree differential equation. Our task with differential equations is usually to find what the function is, because we don't know what it is. Oftentimes, you are given something that we call an initial condition, and that is some additional information that will help you decide on what the actual function is. So the way we're going to use Maclaurin series to solve this equation is we're going to start building the Maclaurin series of the function y based on the definition of the Maclaurin series. So we know that y is going to be f of 0, or y evaluated at 0, plus the first derivative evaluated at 0 times x, plus the second derivative evaluated at 0 times x squared and divided by 2 factorial, plus the third derivative evaluated at 0 times x power 3 and divided by 3 factorial, and so on. So this is the definition that we're going to start with. We are provided f of 0. We know that f of 0 is going to be 1. This is given in the problem. So we already found the first coefficient. Now we want the second coefficient, and for that we're going to need the first derivative. Now the first derivative is given in the equation. So we're going to use the differential equation to substitute the values. We know the differential equation is y dash. We know the differential equation is going to be f dash of 0 will be f of 0 minus 0. We know that f of 0 is 1, so 1 minus 0 is equal to 1. So we have the second coefficient. Now if we want the second derivative, then in that case we go back to the differential equation. We want to do the second derivative, so we're going to differentiate this one more time. So the left-hand side gets the second derivative, the right-hand side gets 2y, y dash, minus 1. When we evaluate at 0, we're going to get the relation f double dash of 0 is equal to 2 times f of 0 times f dash of 0 minus 1. We know these two are 1, so 2 minus 1 is 1. The second derivative at 0 is also 1. Now we're meant to do 6 terms, so let's do those derivatives really quickly. Now, after all this work, we have the values of the first 6 coefficients. So let's put those aside and let's start building the polynomial. The function y is going to be 1 plus 1x plus 1 over 2 factorial x squared plus 4 over 3 factorial x power 3 plus 14 over 4 factorial x power 4 plus 66 over 5 factorial x power 5 plus etc. So here we have the first 6 terms of the polynomial that is solution of the differential equation that was given.